Here we can complete this derivation by using the following identity: sigma AB sigma CD, that is equal to 1/2 eta AC sigma BD minus eta AD sigma BC, and then you have to anti-symmetrizing AB and CD, so there are 4 terms. They are obtained from the first by anti-symmetrization. This you can prove by means of the Dirac algebra. Of the gamma matrices. Basically it says that the commutators of 2 sigma is a sigma. And so once a sigma has a gamma A to the left and gamma A to the right, it gives 0. Once the commutator of 2 sigmas, which arises here, has the same gamma A to the left and to the right, it gives 0, and so on and so forth. Why? How does it arise? For example, let's consider M dm. That is a commutator of, let's write the trace explicitly. TAB, let's recall, adjust the exponential lambda. Let me recall that lambda, yes, this we should have written here, maybe. The matrix lambda is just E to the matrix T. So you have MDM, and dm can only be this, because sigma is constant. That's it. The commutator, again, is a commutator of what? Of matrix. These are matrices, gamma matrices, multiplying it. So that's just sigma AB, sigma CD, TBA, DT, DC. And again, commutator of 2 sigmas is a sum of sigmas, and when you have 2 gammas to the right, to the left, you kill it, and so on and so forth. So this concludes the proof. Okay. So now we have an action that we proved to be invariant under diffeomorphisms and local Lorentz transformations, and that is the action. Now we elaborate a little bit on this omega theta that we obtain, and this thing actually, which we can define as the covariant derivative of a spinor, covariant derivative of a fermion. We have just found it what it is. First, however, let me give you the relation between the matrices sigma and the generators of the Lorentz group. If you take the matrices sigma and you multiply them by 2 minus 2i, you obtain the generators of the Lorentz group. What does that mean? It means that this identity that I just wrote, when you multiply by minus 2a here, minus 2a there, converts into the identity obeyed by the commutators of the generators of the Lorentz group, which is eta BC MAD eta AC MBD eta BD MAC plus eta AD MBC, which tells you that the group closes, namely the commutator of two generators of the group, is a combination of generators of the group, so the Lie algebra if you want. So A, curly A, which is what we wrote previously like that, is equal to e to the minus I over 2 m AB TAB. This is how you write an element of the group. Once you have a representation of those MAB, once you have a representation, any MAB, any kind of matrices MAB that satisfies this, then you have the right element of the group by exponentiating it like that. And you call TAB some number. So for example, how do we obtain lambda? Lambda is minus 1 over, is the exponential of minus I over 2, another representation of the Lorentz group. And recall that lambda is just this. But we can write it in that way. And the representation of the Lorentz group is a matrix. So these are many matrices. So remember, they have an index A and B, but these are not the indices of them as matrices. They have other indices here. Alpha and beta, spin-order indices, if they are built with the gamma matrices. So these are indices, but not of them as matrices. There are many matrices with indices. Here they are alpha and beta. Here instead, the indices are flat-spaced indices themselves. And the representation is just this, which you can check satisfies precisely the commutator algebra of the Lorentz group written there. And so if you replace this m bar here with that, I and minus I gives 1. Two terms by anti-symmetrization cancel the 2, and you get precisely e to the t. Just to show you that these things are interconnected in a general way, and you do not need to do everything all the time once you know what to expect. Now, so the kinetic action of fermions is this. And that we can write by introducing a covariant derivative of fermions, like that. The covariant derivative of fermions is that thing. Partial mu psi plus omega tilde mu psi. And if you want, you can multiply by dx mu both sides and write it as del psi equal to the exterior derivative psi, and then this form. Or if you want, d minus 1 over 8 commutator gamma a gamma b omega ba psi. If you want, have del equal to d plus omega tilde on fermions, on spinors, whatever they are. So if you have a spinor, del psi is a spinor and a one form. And if you want, you can compute del squared psi, which gives the Bianchi identity. That's like a curvature. Del psi is like field strength here. You can interpret it as a curvature. So by computing del squared psi, you study the Bianchi identity for fermions. How is it done? You compute the derivative twice, the covariant derivative twice, because del psi is still a spinor, so its covariant derivative is still the same. Yes, first I write the result. We will check if we need some assumption, namely, do we need metric compatibility, torsionless condition. So, as usual, the Bianchi identity gives something simple, something like that. It's like the commutator, if you want, since these are forms, this is like commuting two covariant derivatives, and the commutator of the covariant derivatives, as you know, gives the curvature. So let's do it. So let's act with the exterior derivative. D squared is 0. So the first term gives two terms. D on this, when you cross omega tilde to go on psi, you are crossing a one form, so you get a minus. Then you have a plus omega tilde d psi plus omega tilde psi. So what you get is d omega tilde plus omega tilde psi. And we just need to show that R tilde is this thing. And maybe find under which assumptions it is, possibly no assumption. So is it true? Let's see. So this thing is, so omega tilde is the trace of sigma omega. So d omega tilde is a trace of sigma d omega. And the rest is, so instead of writing traces, let me write the contraction explicitly, which is better. Otherwise, it's too cryptic, possibly. Plus omega tilde, omega tilde. Let me change page. Omega tilde is, so plus sigma AB, omega BA, sigma CD, omega DC. Okay. So the first one is already okay, because we would like to show that this is okay. R tilde should be trace of sigma R, and R is this. We would like to show something like that. This is again a game of commutators of sigma matrices. So the first one we copy. The second one, observe that you can write it this way. Why? Because the omegas are two one forms. So when you exchange them, you have a -1. And so the second contribution here is this is equal to the first contribution once you exchange those two, which cancel the minus sign. Those are numbers. You can exchange them because they're not numbers, they're forms. So when they have a differential, so when you exchange them, you have a minus sign. But as for the indices are concerned, these indices are explicit, so we can't change them because they are just matrix elements, and they have no other indices. The other indices are spinorial indices in the gamma matrices, and those are taken care by the sigmas and their commutator. But now we know what the commutator is, and so we just introduce the formula for the commutator. So the commutator was what? So it was not that far away, probably. Here it is. Okay. So you have 4 terms. So 1 over 4th, 1 over 2, 1 over 2. And then you have that since all those 4 terms are obtained by the first one by exchanging A and B, C and D, and when you raise both indices or lower both indices, the omegas are antisymmetric in A and B and C and D. And here you see that you need to use this antisymmetry property, which means that we derive the Bianchi identity assuming the metric compatibility, otherwise there is a correction. So we assume metric compatibility. Here you see it. Then all those 4 terms give the same. So you have 4 AC. AC, what is? AC, the first and the third. A and C, okay. And B and D, so A and C. And then you have B and D, which are sigma. Be careful with the indices that we raise and lower. So B is the first index, then I have to write it here. And D is the second index. Now we reorder them a little bit. And check the sign if it turns out to be right. So sigma AB, that multiplies d omega BA plus. So sigma AB, this means that I have to call this A and this B, this will be BB, and this will be A. So I have omega B. Let me write first this one B. Let me lower this like that. C. Then I have this omega CA. Yes, it is right. Now I tell you why it is right. And the sign is right. Because you see, I have to exchange those two indices. And I have to exchange those 2 forms. So there are 2 minus signs, always using the metric compatibility, which is equivalent to saying this, that omega is antisymmetric. So you should remember that. The metric compatibility is the assumption that allows you to say that the spin connection, when you raise both indices or you lower them, is antisymmetric. So we want to exchange those 2 indices because otherwise the contracted indices are not second and first, but second and second. So that doesn't make sense. Well, it makes sense, but it's not the clean notation. So we need to exchange those. That's a minus sign. But you need also to exchange the 2 forms. That's another minus sign. And so in the end, you have sigma AB RB A, and that is precisely what you want. Again, if you do not want to use the metric compatibility, the Bianchi identity will be this plus a correction which will contain the covariant derivative of the metric. It's hard not to assume metric compatibility in this form. So most of the times from now on it will be understood, but not always actually, because next time we will study the gravitational action and we will see all possibilities, even assuming no metric compatibility and deriving the metric compatibility from the field equations of gravity. So in some cases we will be able to derive the metric compatibility dynamically, if you want, from the field equations of the action. So for the moment we have explained how to study the metric, how to couple matter fields to gravity. We will come back to that later, after we will have the gravitational action, because after the gravitational action we will derive the field equations, and we will see how matter affects gravity, the metric, through the stress energy tensor. So we will have to work out the stress energy tensor, for example, of fermions, of scalars, some properties of that. So before moving to the gravitational action, which will take next lecture, the first formulation at least, let's write down the infinitesimal transformations, diffeomorphisms, and Lorentz transformations. Of what? So now we have scalars, we have fermions, we have vectors, we have the metric, the field bind, the metric, the Christoffel symbols, the spin connection. Eventually, possibly you can consider the curvature, whatever you want. So diffeomorphisms yes, there is a pH there, but don't even remember. X mu prime is equal to x mu minus psi mu of x. Psi mu are arbitrary functions that in some sense we understand to be small, and so we Taylor expand and study the first order of the expansion. And local Lorentz transformations. Are transformations that just rotate, so to speak, the Lorentz indices. And if we want that to be close to the identity, it will be something like that. And once you lower or raise both indices, that those parameters will be anti-symmetric. So E prime is equal to E plus this thing. And we again consider theta small in some sense. We already know about the transformation of a scalar. I guess we studied it already, but let's do it again. When you expand phi prime of x minus xi, you have phi prime of x minus xi mu partial mu phi of phi prime is the same up to higher orders. And so you see that you have this transformation. Phi prime is equal to phi plus xi mu partial mu phi. Okay, that's the infinitesimal transformation of a scalar. When you I didn't write the argument because now they have the same argument, phi prime of x, my phi of x, everything is in x. That's how you study how the fields transform when you do not when you do not move the point, or do not change the coordinates. You want to throw the entire transformation on the field. So this is a scalar. Vector. A vector transforms with a Jacobian and again when you here replace x prime with that, you have a mu x minus xi, let's say rho partial a mu. So that's the same as in the case of a scalar, that is replacing x prime with x minus xi and then expanding. But now you have also this object, so you have to compute that object. Okay, so let's compute that object. First we take the partial derivative of x mu prime with respect to x. That's easy because it is equal to what? X mu prime partial derivative x nu, that will be equal to delta, first term. The second term is minus partial mu x mu, x partial nu xi mu. What is the inverse? We want the inverse, the partial x nu partial x, let's say rho prime, is the matrix that plus higher orders, of course. So the inverse is the matrix that gives 1 when you multiply this with that, with itself. So to obtain one, you have to cancel that, and you will have partial psi. Let's check this. If we multiply with that, yes, you have it. It's the only possibility because the indices are arranged like that. So in the transformation of a vector, we have, let's copy this, a mu prime that's equal to, well, first let me move this term to the right hand side, partial psi rho, partial rho a mu. And then you have the Jacobian here, so delta gives 1. And the other one gives plus partial, so 1 partial there is no other possibility than that. So again, this is the Lie derivative. This finitesimal variation is the Lie derivative of the vector. Why did we do this? Because we want the transformation of the filbane, and the filbane is a vector. From a point of view of space-time indices, the filbane is just a vector. Then it has a transformation for the Lorentz indices. But it's just like a vector. So the transformation of the filbane will be this. Exactly the one of a vector, as far as diffeomorphisms are concerned. And as far as Lorentz is concerned, you have an extra piece, that is this theta EB, EB mu. Nice thing about infinitesimal transformations is that when you have many symmetries, the infinitesimal transformations are the sum of the infinitesimal transformation under each symmetry, so there is no conflict at this level because we are just looking at them to the first order. What is the, so plus higher orders. What is the transformation of a fermion? Fermion is, first it's a scalar. Under diffeomorphisms it transforms like a scalar. And then there are Lorentz transformations. Under Lorentz transformation we know that psi prime is equal to a psi, curly a. That curly a is the exponential of sigma ab what? if lambda is equal to delta AB plus theta AB to the first order, that is equal to e to the theta to the first order. So theta is the T, the matrix we called T. And when you expand that to the first order, you get psi plus sigma A B theta, B A psi. So that's just what you add when you have both diffeomorphisms and Lorentz transformations, which means you both act on this and on the X prime, and linearity into the first order does the rest. So plus higher orders. And to conclude, the transformation of the spin connection if lambda is equal to 1 plus theta, omega prime is where omega, here you have theta omega minus 1 minus omega theta, and then here you have plus a d, that's minus actually, minus d theta. Well, you can check that this is just the covariant derivative of theta. Covariant derivative of theta, remember how we defined the covariant derivative of an object? With two indices, you have the exterior derivative, then you have an omega for the first index, if it is for the superscript, and here you have a minus omega to the other side, for the subscript. So it's precisely the covariant derivative. So things conspire nicely to write down nice formulas. So we have done a lot of work, but once you get used to these things, it wasn't necessary. And where gravity is like this, you cannot skip working with many indices. But once you get the basic things, you can save a lot of effort just because you know what you expect. And so even if you can make mistake here and there, you can find where the mistake here is, because the things in the end have to conspire to give something nice. So we'll continue on Monday.